carried out. And that is why they are called predeterministic. Deterministic is final. Before doing that final test with the actual load, this is done at the factory or industry premises. Is it clear? And when we talk about Swinburne test, of course, it is done on a motor. Only one motor is involved in the test, and it is carried out on no load. Obviously, the power taken by the test is very, very small, because on no load, the losses will be very, very less, and hence the power taken by the machine for the test is quite small. That's an advantage. Therefore, it's economical. And the drawback is, in this test, the objective is to find out the rotational loss. And since we find the rotational loss on no load, we assume that the rotational loss doesn't change even with the load condition. But the truth is, the rotational loss will not be absolutely constant, because rotational loss varies with the speed, varies with the load also to a smaller extent. And hence, if you want a perfect performance appraisal or evaluation, this test will not be a suitable one. And number two, the second drawback is, since it is on a no load condition, we cannot see how commutation takes place on full load. Commutation, we know, that's an important process in a DC machine, and commutation becomes very important at a full load, where a large armature current flows, and that will not be seen during the test when we go for Swinburne test. Is it clear? Any doubt here? Okay. Any doubt? Yeah. And further, there are two more limitations. Matter of fact, more than the advantage, the limitations are more. These machines having a constant flux are only eligible for the Swinburne test. That means the iron losses are also taken as constant, for which the flux has to be constant. And that being the case, this test can be carried out only on shunt machines and not on series machines, because in series machines the flux is never constant. And further, we cannot do the test on series machine, because a series machine cannot be started on no load. This we have already talked about. And there must be some load for a series motor to start, otherwise the speed will reach very, very high values. So these are the limitations. And to address these limitations or the drawbacks, Hopkinson test was devised. And this test is also known as back-to-back test, and it's also called regenerative test. Why it's called back-to-back? Because we have discussed the last class. This test involves two machines connected as shown. One is acting as a generator, other one acting as a motor, and one machine becomes output for the other, and vice versa. The motor becomes an output for generator, and generator becomes output for the motor. So in this way, a loading condition is actually practically simulated here, and that is the beauty of this method. So Since we have two machines connected back to back, it's called back to back test. Regenerative because whatever the energy produced by the generator in terms of the EMF will be used to activate the motor, and whatever the torque produced by the motor is used to run generator. So in that way, the energy is regenerated. Therefore, it's called regenerative procedure. Is it clear? Any doubt here? Hello?
No, sir.
It's fine?
Yes, sir.
Yeah. When we do the test, there are two steps to be followed. In the first step, we have to ascertain and confirm that the two machines are in parallel, and that is done by using a voltmeter connected across the switch here. I'm referring to the figure. So when we apply voltage and run the motor, in turn the generator, both the machines will run now, and hence this motor will develop a back EMF while generator will develop an induced EMF. So when the two EMFs equal, then the voltmeter should read 0 if the polarities are okay. If the polarities are not okay, then the voltmeter will read twice the voltage. So for connecting these two in parallel, the condition is that the polarities must be the same, which is confirmed through a 0 voltmeter reading. Is it clear? That is the first step. When that is done, in the next stage, what we do is we put them in parallel and we remove the voltmeter on the switch, and we keep an ammeter to record the current between the two machines. So that, and then what we do, we try to adjust the field current of generator in such a way that the induced EMF of generator becomes greater than the back EMF of the motor. Okay, in which case generate the second machine, that is the one towards right, works as a generator, and the first machine on the left works as motor. And further, to maintain a constant speed, the field of the motor is also varied so that the two machines will run at the same speed, equal to constant rated speed. And further, we see that the current whatever generated by the generator, since it is going to the armature of the motor, this current essentially circulates between the two machines, and hence this will not be reflected in the current taken from the mains. So the current I1 which is coming from the mains will not contain any component of this armature current. Therefore, this current I1 will be quite small because it has to just account for the losses in the two machines. Okay, without considering the output from the machine, because outputs are in tandem. One becomes the output of motor becomes generator, and similarly vice versa. So the input current will be so small. That's an advantage of Hopkinson procedure. Any doubt here? Therefore, by adjusting the field current of generator, we can go on making EG greater and greater than EB, and hence we can adjust the current supplied by the generator. In turn, this corresponds to a variable load. That means we are simulating a loading condition by having two identical machines connected back to back. Is it fine? Any doubt?
No, sir.
Yeah. Then probably this we completed calculation of efficiency. So referring to this diagram, the power drawn from the supply is V into I1. Field copper loss for motor, V into IFM. You see, V is the applied voltage, IFM is the current to the field of the motor. and a field copper loss generator V into IFG, armature copper loss for motor I AM square or AM, that is the current in the armature square into resistance of the armature of motor. Armature copper loss generator IAG square RAG, and therefore the rotational losses of both the machines. Please note, now we are finding rotational losses of both the machines put together is input VI1 minus these losses. And since we have taken two identical machines, okay, rotation losses per machine or each machine is the entire thing divided by 2. So this is what we call P rot, rotational loss. Is it clear?
Yes.
Hello, students. I want others to acknowledge. Vaibhav, Chandramohan.
Yes, sir, it's clear.
Clear, sir. Okay, sir.
Okay. So, if you look at the two testing procedures, Swinburne and Hopkinson, both are meant to find rotation loss only. But the difference what we see between the two is, in Swinburne, the test is done on one machine, which is a motor, while Hopkinson, the test is done on two machines, identical machines, one acting as motor, other one acting as generator. This second point is, in a Swinburne, the P rotational is found on a no load condition, which we assume to be the same even under a loaded condition, which is not absolutely okay or correct. But in this case, the rotational loss is found in the loaded condition itself. Therefore, this is definitely an authentic value compared to the Swinburne test value. Are you getting this?
Yes, sir.
Right. So, with this information, let us look into the calculation of efficiency of the motor. As pointed out earlier, for efficiency calculation of motor, first calculate the input power and subtract the losses from the input to get the output mechanical power as shown here. So, the calculation theme is, for the motor, we know what is the input power. Then you subtract all the losses that should give the output power. And once you know input power and output power, efficiency can be found by dividing one by the other, output by input. So this is how it is done. Total power input to the motor is power input to the field plus power input to armature. Is it clear? Because we have essentially two parts. So one goes as input to the field, other one goes as input to armature. Therefore, which is nothing but V into IFM plus V into IAM, where IFM is the field current of the motor, IAM is armature current of the motor. Is it fine?
Yes, sir.
Now, the losses are VIFM, that is the field loss, IAM square RAM, this is copper loss in the armature, and P rot, which is rotation loss. So all these things put together constitute total losses. Now the mechanical power output of the motor is P input to the motor minus these losses. Is it clear? Once we know P out of the motor, since we know P in for the motor, I can divide one by the other. That should be the efficiency.
No, sir.
No doubt, sir.
Okay. Now, if I have to calculate efficiency generator, For generator, it is we start with output power of the generator and then add the losses to get the input mechanical power and hence efficiency. So for a motor, we start from input, subtract losses from the input to get output. For generator, it is the reverse. We start from output, add losses to output to get input. Is it fine?
Yes, sir.
Right. Like at this point, I would like to know from you why, in case of motor, we start from input, then go to output, and similarly, the reverse for generators. What is the reason? My question is fine. It's clear.
Yes, sir. For the motor, we know the input coming from generator, no, sir. That's why the input is important while calculating the efficiency of motor. Here, the generator, uh, we give importance to output because the output will go to the motor, no, sir.
Okay. Any other answer, students? And what we're trying to do here, we're trying to calculate efficiency. Correct? Understand? Yeah.
Yes, sir. Credits to this.
We are trying to calculate efficiency for which we require several parameters like the losses, the voltage, the current, and all. So, which one is easy to measure? That becomes important for us. The one which is not easy to measure, we need not worry about it. Now, between electrical and mechanical parameters, which one is easy to measure? Question correct.
Electrical, sir.
Sir, I think
It is electrical only, no doubt. If I have voltmeter and ammeter, I can measure the power. Correct?
yes, sir.
But it is not easy to measure mechanical parameter because if I have to find the mechanical power, it is a product of torque and speed. Measuring speed is not bad, it's comparatively easy, but measuring torque is very tough. Therefore, we always choose that which is easy to measure. So, in a motor, the input is electrical, therefore it is easy to measure. I start from input. In a generator, output is electrical, therefore I start from there. Is it clear?
Yes, sir.
Yes, sir.
And this is what we term it as analysis, a higher level of learning. If I just remember that for a motor I start from input, for a generator I start from output, that becomes comprehension or a knowledge. But like I have told this, we'll be giving much importance to the analytical part, problem solving part, and little importance to comprehension. Is it clear? Right. So the output power of the generator is V into IAG. Losses of generator VIFG, that is field loss, IAG square RAG, copper loss plus rotational loss. Therefore, the input now P out plus these losses. Then I can find efficiency. Any doubt?
No, sir.
Other students?
No doubt, sir.
Okay, that's fine.
Sir.
Yeah. Now, some of the important points of Hopkinson test. The test requires small power compared to full load power of the motor generator coupled system. That is why it's economical. Why it requires small power is the generator delivers the power to the motor delivers power to generator, and therefore there is no power required from the mains to activate these machines. These machines, they get activated on their own because they're coupled. So the power taken from the main is quite small. Large machines can be tested at rated load without much power consumption. Is it clear? So that is one important merit. Second point is temperature rise and commutation can be observed because I'm conducting test at full load. That load variation is done by varying the field current of generator and making EG greater than EB. Okay, that's the concept there. And maintained in the limit because this test is done under a full load condition. Therefore, temperature rise and commutation can be observed. Then change in iron loss due to flux distortion can be taken into account due to the advantage of its full load. Since the test is on full load, whatever the change in the iron loss due to flux distortion armature reaction in them. So even that is also taken care of here. And efficiency at different loads can be determined. That means I can go on adjusting EG value with respect to EB value, and hence the current delivered by the generator to the motor can be changed, and therefore the loads can be changed. So that is what we do here. Is it clear?
Yes, sir.
Right. There are certain drawbacks. It is difficult to find two identical machines. Yeah, here the test requires two identical machines. When I say identical, it is very, very difficult to find that equivalence. Please note, I don't know whether you have observed this in the laboratory. If you take two diodes, I'm talking of very small component like diode, the same make, the same type, the same specification, but the two diodes will not have 100% the same characteristic. Have you done any experiment to confirm this in the laboratory?
No, sir.
Yeah, but it's a fact. There will be small difference. And that being the case, when we talk of large machines, though the ratings are same, the specifications are same, but still they will not be identical. So that means the first assumption itself is wrong. Like I don't say it is completely wrong, but it is not absolutely correct. Number two, both machines cannot be loaded equally all the time. Because again, they are not absolutely identical. If they were to be identical, this is fine. But since they are not absolutely, they cannot be loaded equally at all time. It's not possible to get separate iron losses for the two machines, though they are different because of their excitations. Now you see, though we have two different machines, of course, two machines. I don't call different, two identical machines, but still their excitations are not same, and therefore it is not possible to separate iron losses for the two machines. Are you able to appreciate this, students? Hello.
Can you repeat, sir?
Yeah. The it, it is not possible to separate iron losses for the two machines. Let's say we always get the total iron loss, but I cannot say how much is the iron loss for the machine one, how much is for the machine two, because these iron losses cannot be taken as equal in each of the two machines as their excitations are different. If the excitations were to be the same, then iron losses, I can say surely that both the machines will have the same iron loss. Are you able to follow this?
Yes, sir.
Number
Yes, sir.
four, it's quite difficult to operate machines at rated speed because field currents vary widely. Yeah, that is true. You see, once because of the armature reaction at full load, the total flux will come down. Okay, and because again of commutation problem also, the flux will not be absolutely constant. The flux keeps varying because the field currents they keep varying, and as a result, keeping rated speed at all time, it is not possible. It's very tough. So these are the important demerits of Hopkinson. Now we will do some numerical example here. Yeah. Can you please note down this problem? A 220 volts DC shunt motor. Can you go ahead? Are you writing down?
Yes, sir.
Yeah, please do that.
Yes, sir. Over.
Students, hello?
Yes, sir.
Like I'm going to record this, right?
Okay, sir.
Yeah. Yeah. You have noted down the problem?
Yes, sir.
Sir.
Yeah. Okay. Now in the problem, it says the no load input he has given because a 220 volts DC shunt motor at no load takes a current of 2.5 amps. So that means it's essentially Swinburne test, right? So the no load input power is 220 into 2.5. It's okay. $500. Correct, Ann?
Yes, sir.
The shunt field current is 220 by 200. 220 is the voltage across. 200 is the resistance of the field. 1.1 amps. And the armature current under no load is 2.5 minus 1.1 because this 2.5 is the input current. That minus the field current under no load is no load armature current, which is 2.5 minus 1.1, 1.4. Is it fine?
Yes, sir.
Then the armature copper loss is Ia naught square Ra 1.4 square into 0.8. 0.8 is armature resistance, which is 1.6 watt. Therefore, the input power is 500 watt. The machine, it's a shunt motor. It's running on no load. And in this 500 watt, if I subtract 1.6 watt, which goes for the armature copper loss, the remaining is constant loss. It's fine.
Yes, sir.
Now, he says, estimate efficiency of the motor when the input current is 32 amps. So, when the input current is 32 amps, then the armature current in that condition is 32 minus 1.1. That is 32 minus the field current. That comes to 30.9 amp. Now, in this a load of 30.9 amp armature current, the copper loss in the armature is Ia squared Ra, that is 30.9 square into 0.8, 764 watt. Therefore, the total losses now in this load is 764, which is a copper loss, plus 548.4, which is a constant loss, which we have determined under no load condition. Please note, in Swinburne, that is the assumption we make. The rotational loss or the constant loss is the same, irrespective of no load or full load. Is it clear? Serena? Please acknowledge.
Yes,
Any doubt?
no doubt, sir.
Yes, sir.
Yeah. So first we find the rotational loss or the constant loss under no load condition. Then we come to load condition, find the copper loss, add this rotational loss to this copper loss. That should be the total losses under any load. Now the input power is 220 into 32 because he says 32 amps is input current. Therefore, the output power now is input power minus the total losses. 220 into 32 minus 1315 watts. Now I can calculate efficiency as input minus losses, which is output, divided by input. So that comes to 81.3%. ಗೊತ್ತಾಯ್ತಾ ಇದು?
Yes, sir.
Yes, sir.
On similar lines, I want you to do this. You please copy down the problem now, then work out later. Okay?
Yes, sir.
Yeah, please copy down the problem. This is again on Swinburne test, very similar to what we have done the last one. Over?
Yes, sir.
Yeah, so this you please work out later. Now we'll go to a numerical example on Hopkinson test. As a matter of fact, Hopkinson test, the circuit can be rigged up in this way also. Okay, what we have done is one way of connecting the circuit for the test. This is other way. Next class I will talk about this. Today we will take up a numerical example on the test setup what we have discussed. Yeah, this is the one what we have discussed, correct?
Yes, sir.
Yeah. So here we will take up an example on this. Yeah. Please copy down this problem. Hopkinson test on a pair of 500 volt, 100 kilowatt shunt generator. Please tell me when you are when you have completed. Over. Bharati, over.
Yes, sir.
Other students?
Yes, sir. Oh,
Okay. So, motor armature copper loss 230 square, because there's, what is the 230? Yeah. The armature current is 230. And if you look at the diagram, 200 amps is supplied by the armature of generator. 30 amps is taken from the mains. Okay, got it. Therefore, 230 amp is the armature current in the motor. ಗೊತ್ತಾಗ್ತಿದೆಯಪ್ಪ?
Yes, sir.
And that is why we understand here that though the armature current is quite huge, 230 amps, but the input current taken is only 30 amps. That is the advantage of Hopkinson, because the remaining 200 amps is being supplied by the generator. Are you able to appreciate this concept?
Yes, sir.
Okay. So the armature copper loss is 230 square into 0.075 plus 230 into 2. What is this 230 into 2? Hello?
Voltage drop at brushes.
Very good. Exactly. Each voltage drop of brushes is 2 volt per mission. Therefore, it is 230 volts into 2. Is it clear? Like it's 230 into 2. Therefore, the total armature copper loss is 4428. Motor field copper loss 500 into 1.8. Voltage across the field is 500. The current is 1.8. Similarly, generator copper loss, armature copper loss 200, because the generator armature current is 200. 200 square into 0.05 plus again brush 200 into 2. The armature current into 2. Is it clear? Any doubt here?
No doubt.
Then generator field copper loss 500 into 3.5, because the field of this current is 3.5 and voltage is 500. Total copper loss for 2 machines is, we add all the 4, 10,478. Power drawn is 500 into 30. You see 500 volts and 30 amp is the current at the input. Therefore, it is 15,000 watt. Therefore, stray loss for the two machine is 15,000 minus the copper loss. That is 10,478. That comes to 4,522 watt. Since we have two identical machines, per machine it will be divided by 2. 2,261 are there. Any doubt? Hello? Yeah. And this we are going to add to the total losses in the generator. Therefore, 3,400 is the armature copper loss plus 1,750 is the field copper loss plus 2,261 is the stray loss. All put together will be the total losses in the generator. Then generator output is 500 into 200 because the voltage is 500. 200 is the current supplied by generator. Therefore, it is 1 lakh watt. The efficiency now is output, which is 1 lakh, divided by output, again 1 lakh, plus total losses 7,411. Therefore, we start from output, arrive at input by adding losses to the output. Any doubt?
No, sir.
Yeah. Please copy down this problem. Problem 3. Aitana. Over.
Yes, sir.
Yeah. Again, this is very similar to the last one. Can you complete this later? But you have to find efficiency of both the machines now. In the last problem, we found for generator. Now you have to do for motor also. Okay?
Yes, sir.
So I've given 2 problems for assignment. You have to complete it. Next class, I will probably I will close this topic after I discuss about the second, I should say, alternate circuit connection for Hopkinson. So that I'm going to discuss for a small time. Then we will complete, we'll close that topic, and that completes